66 million years ago, the late Cretaceous biosphere was deeply stable. It was a warm, continent-spanning greenhouse environment dominated by immense flora and large mass fauna. That stability was broken by a single physical object, an asteroid roughly 10 kilometers wide. This mass of rock and metal was traveling through the vacuum of space at over 70,000 kilometers per hour. Its trajectory intersected directly with the shallow coastal seas of the Yucatan Peninsula in present-day Mexico. Upon contact, the asteroid's velocity immediately converted into thermal and kinetic energy, releasing a blast equivalent to over 100 million megatons of TNT. The impact functioned as an extreme kinetic to thermal energy conversion that instantly fractured the Earth's geologic state. Within seconds, atmospheric temperatures in the regional blast zone spiked to 600 degrees Celsius across a 1,500-kilometer radius. A supersonic shockwave traveling at 2,000 kilometers per hour swept outward, instantly leveling all geographic features and vaporizing biological life in its path. This diagram shows the global seismic transfer. The strike sent magnitude 11.1 earthquakes ripping through the Earth's crust in all directions. This extreme energy propagated until it focused entirely on the opposite side of the planet, fracturing the crust and triggering active volcanism. Regions like the Deccan Traps erupted continuously, blanketing half the Indian subcontinent in immense rivers of lava. Yet the most significant consequence came from above. The impact excavated billions of tons of rock and water, launching them suborbitally into space. While the regional devastation was immediate, this suborbital ejectoplume provided the transport mechanism to distribute that energy across the entire global atmosphere. 40 minutes after the initial strike, the ejecta cloud reached the peak of its suborbital arc and began falling back to Earth under the pull of gravity. As billions of tons of shattered rock re-entered the atmosphere simultaneously, immense friction superheated the debris. This global map tracks the thermal pulse. The friction caused atmospheric temperatures worldwide to spike up to 1,500 degrees Celsius, turning the sky into a broiler oven. The intense ambient heat radiated downward, igniting spontaneous wildfires that consumed the planet's surface vegetation. Massive surface-dwelling fauna could not escape this radiant heat. Lacking deep shelter, they were lethally exposed to the sudden flash heating. This initial fiery phase acted as a severe thermodynamic filter, effectively sterilizing the Earth's surface within the first 24 hours. The short-term thermal pulse soon gave way to a secondary, protracted climate whiplash. The asteroid specifically struck a section of the Earth's crust loaded with sulfur-rich limestone and anhydrite. Modern geological evidence of this specific crater structure can still be seen in the ring of cenotes spanning across Mexico today. The massive impact vaporized this sulfur crust. High-altitude winds traveling at 6,000 kilometers per hour then distributed the aerosols across the entire globe in a matter of days. This formed a dense, turbulent aerosol shield that completely blocked all incoming solar radiation from reaching the surface. Stripped of solar heat, the global climate plummeted from a blistering furnace down to minus 25 degrees Celsius. This line graph plots the complete thermodynamic whiplash. The massive thermal spike is immediately followed by a steep drop into a deep, sustained freeze. This impact winter stretched from initial months of darkness into a decade-long global freeze. Surviving the intense thermal fire of the first day, photosynthesis. Without light, the remaining continent-spanning forests and vital marine phytoplankton rapidly died off. This illustrates the late Cretaceous food web. Energy flows from a wide plant base up through a middle tier of herbivores to apex predators. The loss of photosynthesis triggered a strict bottom-up collapse. The base layer of flora turned gray and crumbled away. Deprived of vegetation, the massive herbivorous dinosaurs systematically starved to death. The apex predators followed shortly after. Their immense bodies required thousands of daily calories that no longer existed in the ecosystem. Highly mobile, airborne predators succumbed as well, as powered flight demands immense metabolic energy reserves. Large body mass, which offered the ultimate evolutionary advantage during the warm Cretaceous, became a fatal liability in a zero-sunlight environment. The Cretaceous-Paleogene boundary acted as a strict biological filter, strictly selecting for specific physical traits. This filter resulted in a 90% extinction rate, eliminating almost every terrestrial organism weighing over 30 kilograms. Which raises a mechanical question: how did marginalized, rat-sized mammals and small amphibians survive when the apex predators failed? This cross-section compares surface extremes with underground stability. Soil and water act as excellent insulators, a process known as thermal buffering. Early mammals actively utilized these subterranean and aquatic margins to hide out, completely bypassing the extreme atmospheric heat of the first day. As the impact winter dragged on for years, their small mass required very few calories. They survived by scavenging on a diet of insects, roots, and dead matter. Mammalian survival was the result of a specific mechanical advantage, using low mass and thermal buffering to outlast a global collapse. As decades turned into centuries, the high-altitude dust and sulfur ash finally began to settle out of the atmosphere. This settling ash left a permanent geologic scar in the rock record, recognized today as the KPG boundary layer. Below this distinct iridium-rich line, dinosaur fossils are abundant. Above it, they cease to exist entirely. With the ash cleared, sunlight finally warmed the earth again. Dormant seeds buried safely underground began to sprout in the nutrient-rich ash, restarting photosynthesis. The surviving mammals emerged from their burrows into an ecosystem completely wiped clean of large competitors. This vacant landscape triggered a massive mammalian radiation. These survivors rapidly evolved, increasing in mass and diversity to fill empty ecological niches across the globe. The Chicxulub impact functioned as a selective mechanical filter, removing the established megafauna and leaving the planet's vacant niches to the mammalian survivors.